Previously, we talked about micellization, this process by which we have a hydrophilic head group and a hydrophobic tail group. They come together to form a bubble to wash away dirt or grime or grease in a soap molecule. And this is really similar to the way that the lipid bilayer that makes up cell membranes is constructed. This is the wall, or membrane rather, I should say, that determines what enters or leaves the cell. We have this double layer of phospholipids, which are shown here, that arrange themselves with their hydrophobic tails pointed inward and the hydrophilic tails outward. This gives a lipid membrane that contains the cell and also means that the outside of the cell is water soluble, which is of course very important because we have cells that are transported through blood, things like that. Our biology is a watery world, and it's important that the cells adhere to that. And so the key to this is what's called a phospholipid. And so in order to look at a phospholipid or a phosphoacylglycerol, what we're basically doing is we're taking that triglyceride and we're sticking a phosphate group in the middle. This phosphate group ends up being nonpolar and is what defines these phospholipids. And so here's a better look at one of these phospholipids. And so remember before, right, we still have two of the regular old chains, right? And let's examine this on the left and try to see that glycerol in the middle. This is that anchor that's in the middle there. Those are those 3 carbons for which we mounted 3 different fatty acid chains. And if we look at the glycerol and look downward, well, we still have 2 of the fatty acid chains, 2 hydrophobic tails, they're right there. But what we've replaced the third one with is a phosphate. And a phosphate is a polyatomic ion that has a charge on it. And because it has a charge on it, this means that it's really much more associated with being polar than nonpolar. And that means that the head of this phospholipid is polar. It may look like it's a lot smaller than the long fatty acid chains, but remember that phosphate is a pretty big atom, as are the oxygens. And so what this gives a phospholipid is this big polar area that makes up the hydrophilic head group. In accordance with this, it's able to construct the phospholipid bilayers. Now we have a hydrophilic head and a hydrophobic tail, and it works a lot like a micelle, creating, though, a slightly different structure to make up the cell membrane. And so again, this is just a bit of a breakdown of triglycerides versus phospholipids. Triglycerides have 3 fatty acid groups and are really, for the most part, nonpolar hydrophobic, whereas a phospholipid has a phosphate group plus 2 fatty acid groups, and that makes up membrane structure by its hydrophilic head and its hydrophobic tail. Furthermore, the structure of this cell membrane doesn't just keep things out, right? This facilitates a lot of important transport for the cell. There are some molecules that can diffuse through the lipid bilayer, right? It's not like it doesn't let anything in, so some things can just diffuse through the bilayer. Other things it facilitates, and so we have membrane proteins where we have little channels basically that are allowed to accept certain other molecules into the cell based on the needs of the cell. And finally, we have active transport, where we can put energy in order to pump things in or out of the cell. Other membrane proteins can accomplish this. We'll look at proteins in the last module of this course, and we'll see that proteins do all of the kind of fancy work of biochemistry, right? I mean, lipids do some fancy work too, but we'll see that proteins have this huge range of functions, including this very specific need for the cell membrane, that is to facilitate transport in and out, as well as actively transport other things in and out.